So let me go to a new page here. So it's simple. You go to desmos.com. Right, and you'll see an option for a graphing calculator. Right, you're gonna want to sign up. Right, if you don't have a login, you're gonna want to sign up. The sign up process allows you to save your work. Right, you can't save your work unless you're logged in. Right, but when you sign up, you can link it to an external account. I mean, you don't have to do it from scratch. So you got to do the I agree, I read and understand, but I signed up with Google, right? So I don't have to create a new login for my Desmos account. I just link it to Google, right? You can link it to Apple too. The benefit of linking it with Apple is, as far as I understand, they have a little bit stricter regulations in terms of sharing information with third parties. So that makes people feel, warm and fuzzy. So a little bit more secure. So maybe that's the way to go. But I just did it with Google. Right. So I'm just going to log in because I have my account. All right. And when you're logged in, you just tap on graphing calculator. Now there are other types of calculators that Desmos has, but we'll just use graphing calculator for the time being. All right. It's a very flexible sort of calculator because you wouldn't think so based off what you see on the screen. It looks like an ordinary calculator, but there's a lot of hidden functions that Desmos will allow for that maybe you wouldn't think are possible on a free online calculator. Right, emphasis on the free part of it. Right. In this function menu, you have all these different options. Now, a lot of this is going to be irrelevant to us at this point, but if you plan on taking other math courses, like maybe a stat course, you can see that there's a lot of stuff here related to statistics. And then there's some visualization stuff, also statistics, a lot of statistics, some calculus, a lot of stuff that we'll never really discuss, but then you get into like the geometry stuff, and it's like, oh, how nice, they have some geometry here for us, right? But these functions are the obvious things. There's so many other things that Desmos will allow for that it makes it a really useful tool, right? So I'll talk to you more about this as we go, but for now, we'll just use it for simple computations, all right? Anyway, and it's accessible on a phone. I found that I didn't really need the actual app, just the online, the web version of it is fine. In fact, it's good. It doesn't glitch. I find that the apps tend to glitch a little bit, but I'll let you decide. Right. To get started, we're going to talk about a little bit of vocabulary. Simple stuff, the assignment, that first assignment was really like the entire unit's worth of vocabulary. We're only just focusing on a couple of terms here, right? So point, line segment, and angle, right? An interesting thing about a point, like we tend to think of a point as just as a dot, but a point actually has no size, right? So it's just an indication of a position, on a graph or even on a sheet of paper. So, like, for example, if you look at one of these diagrams here, like the one that has AB, those points there, they don't really exist. Right? There is some location, some theoretical location, if you will, and indicated by that, it's indicated by that point, that quote unquote point. So I kind of look at it, or I think of it as a X marks the spot situation. Like if you're searching for buried treasure, you'd see an X on a graph, or on a map indicating a location that you should go looking to dig for your buried treasure. but you would not expect to find a big X on the ground, right? You wouldn't even expect to find a point marking that location on the ground, right? But you would know that there is some point that you must be aiming for in order to start digging and find that buried treasure, right? So it's more like if I were to, even on this graph here, say, I'm thinking of this point right here, right? And you're like, which point are you talking about? I'm like, can't you tell I'm pointing it? Yeah, it's right there. And you're like, well, you're not showing us anything. So that's because the point doesn't really exist. But if I plot the point 2, 2, and tell you that that's the point I was indicating, then you say, oh, okay, but there's still nothing really there, right? There's nothing at that location. I'm just saying, train your eyes on that spot. What spot? The one I'm pointing to right now. All right, let me just make a little mark there for it. That location, all right? But there's nothing really there. Right? So it's very philosophical, but and honestly, this is probably the most discussion anybody's ever given you about the definition of what it means to have to be a point. But since a point is basically a circle, I mean, this is mind-boggling too. It's a circle in which the radius is equal to 0. You know, like if you think about what a circle would look like, I'll just draw the graph of the circle. You know, that's the graph of the circle. You know, forget about like how I generated that. You just see a circle on the screen. Okay? That's wonderful. It gets bigger. It can get smaller. What I'm saying is that a point would be the instance in which that radius is equal to 0. And you're like, oh, so nothing. But yeah, but it's at a location. It's right there at 0. Right? So there's some point there. So I'm pointing to the location, but there's nothing there because the circle doesn't have a radius that exists anything bigger than 0. Right? So it's really kind of fascinating in that regard because it's like, oh, we've worked with points, you know, in the past. You know, think about other math classes you've taken. You plot a point on the graph, and it's like, no, there's definitely something there, but it's not really actually the case. Right? And when we start thinking about different dimensions, it really starts getting a little crazy because a line is a straight definition, straight one-dimensional figure that has no thickness and extends endlessly in both directions. Right? So this thickness that I'm referring to here that doesn't exist looks very clearly on paper as if it does have some thickness. I mean, we're looking at this distance here. There's a little bit of a lag, but this distance here is being the thickness. But really, that line doesn't exist either. It's just indicating just a path. So if I tell you to get up and start walking in a straight path and never stop walking, you know, like X-Men Origins Wolverine, like one of the worst movies of all time. But if I tell you to start walking and never stop walking, that doesn't mean that there's a line on the ground indicating your path. It just means that you're walking along that path. That path could be really wide. It could be really narrow. It's just a path, right? So it's really, again, like I said, philosophical. So then you're looking at points A and B that have no thickness, no width on a line that has no thickness. It's like, okay, so what are we even doing? Okay, so the way we name a line is based off of those points that are on the line. All right, so any point that exists on the line would be the components of the name. So we would call this line AB, indicating 2 points on it. But then we would put a little image of a line up right overhead. All right. So that's how we would name line AB. And this is how we would name line CD. Or well, the second line, which would be line CD. I watched, I mean, it was really old. It was Carl Sagan. But a discussion of different dimensions. It's like, what would a two-dimensional universe look like? Like, I can't even fathom what a one-dimensional universe would look like, but it was really, really fascinating because if you look at, let's say, we'll just draw a three-dimensional solid. It doesn't really matter. So let's say you have a cube. This is always an adventure, me drawing a cube. Don't let the autocorrect fool you. You know, that was terrible. Okay. So that's the best I can do with a cube. Right. It's actually not terrible, but it is what it is. You know. So what would a two-dimensional cube look like? Well, that's the issue because a three-dimensional figure has just that, 3 dimensions. The 3 dimensions in this case, length, width, and height. All right. So if we wanted to bring this down to 2 dimensions, we'd have to get rid of one of these. So maybe we get rid of height. So 2 dimensions. We'd be looking at the length and the width only. Now, in this context, that should make some sense. You know, you figure 3 dimensions, you know, length, width, and height. You get into 4 dimensions, like, oh, what does that even look like? And that's a trickier situation because it's just another variable. Like, what would that other variable be? It all depends on the situation, right? But if I got rid of height, then I would be looking at really just this piece here. That would give me 2 dimensions. Okay, so we just take the floor. You know, like if that cube represents a room, you know, it's like what would an example of 2 dimensions be? The floor, the ceiling, one of the walls. Okay, because who's to say you can't get rid of length? You know, so every one of these, you know, any one of those 2-dimensional things would be known as a plane, right? And what really is a plane except different lines, because this could be infinite. This could go on forever. 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 In each direction, in each relevant direction. So you'd have your lines and the need to name those lines based off of whatever these dimensions are known as. Right? But it could actually have gone this way too. And but that would be just another drawing. So so that's a little bit of a glimpse into the world of two dimensions. But then you start asking yourself, I'm just cleaning this up a little bit while I talk. You start asking yourself, what would a human look like in two dimensions? Well, you'd have to start thinking, okay, well, if we're going to compare it to this situation, what did we do? We took the floor. We had, I always think I can multitask, but I really can't. Right. So let me just finish up this diagram. Yeah, so when we took the cube and we wanted to just decompose it into two dimensions, we just dropped the height, right? So what we would say is, okay, if it's a human being without height, what would we be looking at? It would really just be a cross section of that human being, right? But if we're using this idea of two dimensions being the floor of the cube, then two dimensions would be the floor of the human being. Now, I barely drew the cube, so there's no way I'm drawing a human being. But if you think about the footprint of a human, you know, I'm not talking about footprint in the sand or anything like that. I'm talking about, like, you know how they make the fingerprint, but do that with a foot. That would be a human in two dimensions, right? And in fact, if there were organisms or any kind of life that lived in two dimensions, if a human came walking by, all they would see would be that footprint. Right? That would be the only thing that would exist in their universe. Right? But in order to understand things like this, we'd have to understand not only how to name points, lines, line segments, and things like that, but also like what they are. Right? And this concept of one-dimensional versus two-dimensional and things like that. Right? So when we get to a line segment, we're just talking about a part of a line. Right? So if I'm looking at this as an example, let's say I call this point A, this point B, C, and D, very creatively, then this little line segment here would define the entire line that it exists as part of. Right? So this would be line AB. Same idea here. This would be line CD. Then we'd have line AD and line BC. Right? But then we could also just be talking about the line segments themselves. Right? Well, what if we don't want to go all the way on that infinite line, the one that goes forever in one direction, forever in the other direction? What if I literally just want to start at this location here and stop at this location here? That would be a line segment. Right? Part of a line with two endpoints. Right? So it's actually pretty easy to name a line segment. And the line segment is just the figure itself, or the values that make up the figure itself, is with a little line segment over here. Right? So I'll just go to this example here. Line segment AB would be this little pathway here. It's not infinite. It's not going forever on in that direction or that direction. So I'm just looking at line segment AB. So give it a little bar over. Right. For those of you who have experience with statistics, you might be familiar with the symbol for a mean, X bar. The same kind of notation. Just a horizontal line right overhead. Right. So then this one would be BC. CD. running out of colors, so let me just re-up on a fresh set here. AE. And I'm gonna go with the green for those students scored home. Now you can name a line segment in any order. I could call it line segment AB or BA, for example. We typically want to go in alphabetical order. I'd call this one BE. Oh, geez. Shaky hand. Autocorrect. So naming the line segments isn't really that difficult as long as you know where it starts and where it stops. Naming angles, it's not too bad either. It's the same idea, except you'll have an additional component. So an angle is a space usually measured in degrees. Another term called radians that you can measure in, but we're going to focus only on degrees, or at least for the majority of the course. Between two intersecting lines or a surface, or surfaces at the point where they meet. An angle is denoted by a symbol. It looks like a little less than symbol. But yeah, it's got a little flat bottom there. Followed by the three letters which represent the points that form the angle, with the middle letter being the point located at the angle. Right? So for this diagram, let's say I'm focusing, we'll go around and do each one. So let's say I'm just at this moment focusing on angle B, or at the angle at B, is really what I should say. All right. We use a single arc to indicate an angle. Right.
Why am I recording it?
Oh, sorry, I thought that might have been a question. No. So anyway, the single arc to represent the location of the angle in question. Right. So what we do is we start with the line segment leading into that angle, and then the line segment coming out of that angle. Right. So for instance, this one would be angle ABC. All right. When you're freehand writing this kind of stuff, it's very often that your angle symbol is going to look like a less than symbol. That's not a big deal. Right? I mean, if you can make it look good, that's even better. It should be horizontal at the bottom, but maybe we'll try it again. Little autocorrect goes a long way. My notes would be a disaster if I didn't have that ability. So, going around, I got three other angles here. Now they all look like they're of differing size. Right? They don't look like they're the same size as one another. So I wouldn't want to use a single arc to represent this angle here at C. I'd use two arcs to indicate that they're going to be different measures from one another. Right? That's something to keep in mind, because if I have two angles with the same number of arcs, like for example, if I put a single arc here, I'm telling the reader that this angle has the same measure as that angle. So they would be the same size. I don't know that for sure, so I'll give them all a different number of arcs. That could be annoying if you have 16 angles, because then you'd have to have like 16 little arcs if they're all different size. But that's not going to happen. At least not in this class. Not on my watch. Okay, so this angle here at C, you're coming in, starting on the line segment, going from B to C, then going from the line segment from C to D. Okay, so this would be angle BCD. All right, you could also say DCB. Right, but the key ingredient here is that C needs to be in the middle. All right, because that's the point where the angle exists. All right. Then, continue working your way around. I'll go purple. So I'm looking at this angle now. Oh, that's fun. Didn't mean to shade it in, but that's okay. So this one would have 3 arcs. The more arcs you draw, the tougher it is to make it look nice. Right? But I'm starting off on the line segment going from C to D, then going from D to A. Or I could say I'm going from A to D and then D to C. Either way. Right? So this would be angle. Pick whatever one you like, C, D, A. And then the one last one here, I'm going to go, I think the thing this color would be nice. So starting off over here, going from D to A and then out to B, we'd have 4 arcs here. And that would be angle DAB or BAD. All right. It seems like a weird thing to spend this much time on, like how to name the sides and the angles, like line segments and angles. The thing is, we're going to be referencing this so frequently. And when you have problems that say, given angle DAB, and you don't know which one it is, and you start thinking, okay, well, maybe it would have been worth it to spend this amount of time on it, So that's a little bit of the structure of shapes and the angles and the line segments and things. Right. We're also going to talk about measurements. Now, there's different ways you come up with measurements because really there's 2 types of geometries. Well, there's multiple geometries, but there's 2 types of geometry that we'll focus on. And one is what's called Euclidean geometry, and the other is Cartesian geometry. Right? So what you're seeing on the Desmos screen is an example of Cartesian geometry, okay? Because that's the case where you're looking at coordinate planes. I mean, we can get shapes on coordinate planes. You see one right there. That's not really too challenging. I could even make a graph of a polygon, the multi-sided figure, closed-in figure. If I wanted to plot some points, let's say 0, 2. I call that point A, just for the sake of having a name for it. Then I can plot one, let's say at 2, 4, call that point B. And then maybe, I don't know, they'll do one more, point C. We typically go, I mean, it says it in the notes, but we typically go capital letters to represent points. Right? So C, I'll say it's like 2, 0. Now, this should have been something you've seen before, the idea of plotting points, but just in case, because sometimes it slips through the cracks, when you're dealing with a coordinate plane or coordinate axes, X and Y axis, the way we plot points are X value followed by a Y value. So the left, right followed by the up, down, right? So if I say 2, 0, I'm saying going right 2 units, go up or down 0 units. So don't go up or down at all, right? The 2, 4 is the same as saying go to the right 2 and go up 4, right? It's a movement. It's a horizontal movement followed by a vertical, right? But then in the function menu here, in that little section that they reserved for us, you have the function polygon, function. If I just put in the vertices or the points that make up the polygon, it'll plot it for me, which is really nice. Right? We could also determine measures based off of that. Like, for example, just going into this, I could say under functions, it gives us an option for distance. I could say, all right, well, tell me what the distance is between point A and point B. And it'll just flat out tell me that numerical value. That's what you would get if using a scale drawing of this, if you were to take a ruler and measure the distance from point A, which was this point here, to point B, which is that point there. All right. So it's nice to have technology do that. You know, there's so many different things that Desmos will do for you. Right. And this is just the tip of the iceberg. Right. Later on, I'm going to show you how we can use protractors and rulers using a Desmos graph. And it's interesting stuff. But you know, that's all stuff that we can do. But like you have this diagram here, and it says, you know, find the distance between A and B. They're like, oh, well, I suppose I don't have to get a ruler out now and measure. Maybe I just can use a function in Desmos to do that for me. Right? So we get a little bit of both in this class. Right? If it were an in-person class, I would have my set of rulers and protractors. But in this class, I have a set of rulers and protractors. They're just all digital. Right? But more on that later. So linear measure and precision. Right. So a little blurb here. The precision of a measuring instrument is determined by the smallest measurable quantity. I mean, it's a wordy way of saying, what's the smallest increment on your ruler? And what is that worth? You know, so if you're used to, you know, tape measures, you know, working around the house, woodworking, whatever, you know, anything that would require you to get the old tape measure out, you're probably used to 16ths as a measure. You know, like the smallest little increment is the 16th. You know, so that's a possibility. When you're dealing with a meter stick or something that's in metric units, the smallest increment would be a millimeter. Right? So, yeah, a bunch of different examples here, but that's the idea. What's the smallest little increment that you could have? That's what we talk about in terms of the precision of the ruler. So when I look at number one, I'm looking at just that first little tick mark here and asking myself, what is that one worth? You know, what is the value of that first little tick mark? That's the scale. That's the precision of the ruler, right? So I look at this and say, all right, well, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 tick marks. I'm pretending that we don't know what a millimeter is, but you know, just in case, maybe you don't. There's 10 of those little increments there. So we're looking at 1/10 of a centimeter. Right, 1/10 of a centimeter, which is the same, or you could also write it as or. .1 centimeter. That's all right because you can use the technology to help you get the sense of that, right? But in this case, when you're talking about 1/10, put it in decimal form, 0.1. It's like, oh, why do they call the first decimal place the 10th place? Well, that's because the smallest increment of one decimal place is 0.1, which is in fraction form called 1/10. That's why it's the 10th place. If I had a 1/100th, the second decimal place, we call that the 100th place, right? And it makes sense because the fraction form is 1/100th, right? This is, you know, it's slowly getting into the realm of like, you probably know all this stuff, but I can't take the chance. You know, I don't want down the line to regret not having explained all this stuff. That's not white. I wanted the white mark. There it is. But still not white. Why is, oh, because I have a highlighter on it. That's the one I want. I'll lock it in, and there we go. I had a stray mark there when you get rid of it. All right, so the precision of the ruler is 1/10 of a centimeter. Now you might say 1 millimeter. Sorry about the lag. I don't know what the story is there. I mean, I think I do, but I'm not 100% sure. We got the Zoom going, share screen with an iPad, while also having my Google and my Blackboard open. And full disclosure, I got my my YouTube going on in the background on the Apple TV, so bandwidth is an issue. And I'm also really convinced that somebody's stealing my internet, so I gotta figure that out too. So anyway, different problem for a different day. So anyway, what we're looking at here, we have 2 followed by 1, 2, 3, 4, 5 of those 1/10. All right. So 2 plus 5 of those 1/10. All right. When you're finding a percent of something or a fraction of something, that's an indication of multiplication, right? And also, you know, the directions here say find the length and the precision of the object. So it's like, all right, we know what to do here, but the notation also tells us to do that as well. All right, that little m here means the measure. All right, and this is segment, line segment, really. For short, we call it segment. You know, so if you hear me say segment instead of line segment, I'm saying the same thing. All right, so line segment AB. All right, it's a nice shorthand way of saying, you know, or asking you to do something. You know, I don't have to give these entire instructions. I could just say M of AB. Right? So 2 plus 5 times 1/10. Well, 5 times 1/10 is 5/10. 5/10, which is 1/2. So 2.5. But you kind of knew that just by looking at the picture anyway. Right? So you would say 2.5, 4, 2 5/10, or you could just say 2 1/2. They would all mean the same thing, but that precision value is the 1/10 of a centimeter. All right. And the importance of the precision of the ruler is, I mean, I don't want to get too much into like what would be covered in other courses, because that's not really the point. But you know, you have different types of information, and sometimes information is dependent on the nature of the measuring instrument. Right. So a more precise ruler might have given a different measurement. A less precise ruler, same deal. Right? So it's kind of like if you're weighing something. You know, like if you have a crappy scale, you know, you'll get in the neighborhood of what the weight is, but it's not going to be as precise as a scale that goes to like the nearest 100. You know, so that's the idea there. You know, and in this case here, you know, case in point, the precision of this ruler, one little tick mark is 1/4 of 1 unit. So this one little tick mark is 1/4 of an inch. So that's the precision of the ruler. All right. So it's not very precise. Now, beyond the 2, I have only one of those tick marks. That's a distance of 1/4. So 2 and 1/4. 2 plus 1/4, 2 and 1/4. All right. 2 and 1/4 what? 2 and 1/4 inch. All right. But if I told you that the actual length of this pencil is 2 5/16 of an inch, you know, you could look at it and say, okay, maybe, but I only got this ruler to work with. So how would I have been able to figure that out? Can you imagine that on a test or something? I mean, we test in this class, but like if you were given this ruler and you put down 2 1/4 inches, and then you got marked wrong because the answer was actually 2 3/16. Like how would I have been able to find that out? Oh, didn't you know you should have brought your own ruler? Well, then why'd you give me this ruler? You know, like if you wanted a more precise instrument. You know, so that's a lot of the thought that goes into it. The more precise the instrument, the more precise the measurement. Right? So case in point, number 4 is consistent with number 2. Number 3 is pretty much the same idea as number 1. Right. So again, 1/10 of a centimeter is the precision of this ruler. So then I'm just going beyond the 5. 1, 2, 3, 4, 5 of those tenths. Or 5 1/2, or 5.5.
Professor?
Yeah.
Sorry, I just have a quick question.
Sure.
In terms of answering these, would you prefer us to answer, like to write it in decimal or fraction, or do you not have a preference? Because like for the precision of the ruler, you've been using a lot of fractions, but my mind immediately goes to decimals. I just wonder if you had a preference.
No preference. Yeah, I'm just putting down the different choices just based off what you're saying. You know, like some people's mind take them in one direction versus another. So you get different options, you know. So if you're a decimal person, then go for the 5.5. If you're a fraction person, go with one of the other choices, but no preference on mine.
Gotcha. Thank you.
No problem. Okay. So number 4, that's the more precise instrument, or in this case, ruler, using standard units. So each tick mark here, you know, like it's gonna have a value, and it's all dependent on what fraction it is of the whole. So I have 1, 2, 3, 4, 5, 6, 7, 8, and then 8 more. So this is going to be 1/16 of the unit. So in the unit, the single unit is 1 inch, so 1/16 of an inch. Right? Now, in this case, you might find yourself going more and more towards the world of fractions, depending on where that F gets placed. Okay, because 1/16 in decimal form, I mean, it's fine, it rounds, but it's not as clean as like a 10th, which is why like the entire world prefers the metric system, you know, instead of, you know, like what we prefer here. Do we even really prefer it? No, we're just used to it. That's all it comes down to. You know, because you still got to do the mental math. If it's like, all right, the speed limit is 100 kilometers per hour. Like, all right, what does that equate to in miles per hour? Because that doesn't make sense of what that is. So it's just what you're used to. If you grew up on the metric system, then you look at that as being the obvious choice. Right? But the precision of the units, the instrument here is 1/16 of an inch. And so beyond the 1, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of those 16ths. So 1 11/16 inch. Now, in decimal form, 1 plus 11/16. Okay. And by the way, I mean, this is something, again, that maybe you knew, maybe you didn't know. I'm going to say it anyway. A mixed number, the way you figure out the decimal form, or at least the most convenient one, is whole number plus the fraction. Right? We write it as 1 11/16, but it's really 1 plus 11/16. Right? So we could also write this as 1.6875 inches. All right. So then what does the measure of CD equals 1.25 inches mean? Like, oh, okay, so now we're getting philosophical. So what we're looking at is a measure of precision, because if you go to the decimal values that we were looking at here, you know, just for each problem, we had a 0.5. This one could have been a 0.25. You know, for some reason, I didn't write the decimal equivalent here. So 2.25 inches. (1.6875 inches) and 5.5 inches. Right? The decimal value gives you a clue as to the precision of the instrument. Right? So what are we measuring in? The first one was in number one, it was the precision of 1/10 of a unit, or 0.1 units. Right? And it took 5 of those beyond the 2 to get to where we wanted to be. Right? So in this case, if we just focus on the 0.25, what we're saying is that the precision of the instrument the precision of the ruler would be 0.25 inches. Okay. And so the measure of CD being equal to the 1.25 inches, that 1.25 inches is the same as 5 0.25-inch increments. Right? You know what? Instead of the dash there, because that looks like subtraction, I'm just going to write out the word 5. Right? So basically, it's saying that we're counting in terms of whatever the precision is. How many of those increments did it take to get to the 1.25 inches? 0.25, 0.5, 0.75, 1, and then another 0.25 gets me to 1.25. It took 5 increments of 0.25 inches to get where I wanted to go. All right. So yeah, it's a different way of looking at it, but it definitely brings a little bit more meaning to what it is you're computing when you're actually measuring something. Right? It just might go under the category of things that, you know, it's stuff I never ever wanted to know. Or maybe it's like, yeah, I think I knew that the whole time. I don't know that I ever needed to have it spelled out for me, but you know, it's a good thing to talk about in class on a Wednesday evening in the beginning of a course on geometry. Yeah. Number 6 seems to come out of nowhere. That means that I forgot to type something. That the notation. There should have been a page in here on notation, so I guess I'll just be doing it on the fly. The little equal sign, the little squiggly jammy on top of it, that means, well, it means 2 things. If I can get an equal sign, for whatever reason, I can't function in terms of writing. I should have just done a copy paste job on it. All right. All right. I got there. This means congruent. Right? Congruent. Some people pronounce it congruent. It sounds ridiculous. I mean, congruent doesn't sound much better, but at least it sounds like more fluid, I guess. Congruent. Great. It's a word. Another word. More vocabulary. That's great. So that's what the symbol means in terms of like a real word. but congruent means geometrically equal. All right. Which needs to be explained also, because it's like, okay, well, now that we know that that symbol means congruent, which in turn means geometrically equal, by logical reasoning rules, we could say now that this means this. That's great. But then you have that question of what does it mean to be geometrically equal? Generally, it means that we can make a statement about two sides, two lengths, two angles, whatever, having the same value without knowing what that value is. Right? So, like, for example, I'll just do something kind of obvious, I think, anyway. And at least when you see what I'm doing, it should be obvious. I'm going to make an angle here. I'm going to call that angle ABC. At least I will in a second. I'm just going to do a little copy job real quick first. All right. So I'm going to call that ABC. Okay. So I copied it. Now I'm going to paste it, creating another angle that, because I did a copy paste job, I know dang well that this angle is exactly the same as the angle that I drew initially. So this angle here is going to be the same as that angle there. So let's call this one DEF. I didn't measure these two angles. I have no idea what their angle measures are. I mean, when we learn a little bit more about angle measures, we'll be able to make a statement about that. Like acute or obtuse and things like that. But at this point, even though I can't tell you what number represents that angle, like is it a 20-degree angle or a 50-degree angle, I can tell you that ABC is congruent to DEF. All right, so I'll call this example. Make it look all nice like. All right. So that's an example of congruence. I don't know the numbers, but I do know for a fact that they have to be the same line. I'm sorry, the same angle. Just because I did a copy paste job. They have to be the same. Because one's a duplication of the other. Like if you draw a diagram on a sheet of paper and then run it through a photocopier, you expect that diagram to be the same and all the corresponding measurements to be the same. I see something in the chat here. Oh, sorry, that was old. My bad. So to answer number 6, they say if CA is congruent to BO. So somebody comes along and says, you have two line segments, one of them CA, the other BO, they're the same length. And then somebody else says, oh, by the way, the length of CA is 0.6 centimeters. Then we now know that the length of BO is also going to be equal to 0.6 centimeters. So number 7 is basically the same thing. We're looking at, these two measurements are congruent to one another. They have the same value and same unknown value. A little typo here. This should say the measure of side and or line segment ME. So let me just make a little adjustment. I don't recall if I talked to you about typos for bonus credit. It doesn't sound familiar. I always try to make it a point early on in the course to do that, and then I usually forget. until I realized that I made a bunch of typos, in which case it becomes relevant. Right? So what I do is for bonus credit, I offer an opportunity. Right? And so what that is like here, I made a typo, right? So I corrected the typo on this PDF version of the notes, but I need to also make the adjustment on the master copy, but I'm not going to remember to do that. So I need help. So what I ask is that if there's a typo, if somebody sends me an email with that typo, so in this case, it would say in the notes from today's date or whatever, on page 2, there was a typo in number 7, right? It's first come, first served. So what happens is you send me the email. If you're the first one to send the email, I look at the timestamps. I first make the correction to the notes so I don't forget. And then I give you 1 bonus point. Right? If you're not the first one, you don't get the bonus point back. But I make so many typos that don't worry, there's plenty to go around. Right. So after you reach 3 bonus points per marking period, wrong school, per unit, then you're done for that unit. So you get an opportunity to earn 3 bonus points per unit just by submitting typos. All right. So again, that's just like if you notice them on your own, that's even better, because the ones that I point out, everybody says, "Oh, I'll just send the email real quick and that'll be fine." It's the ones that I don't notice. Those are the ones I really need the most help with. But I'll take punctuation mistakes. I'll take grammar. I'm just terrible with. Things like this that are obvious. I'll even take things like, how I drew this side example. I just made an example. It would be great if that was actually part of the notes in the future semester. Anytime I have like a whim or on a whim, I create a new example and I throw it down in the packet, I need a reminder to update my notes for upcoming semesters so that everything is like a little bit nicer. Right. So yeah, you can get as many as 3 bonus points per unit for doing that. The other thing is that, and I don't have it set up for today, but I'll also be doing what I call the word of the day. I mentioned that you do have the YouTube bonus opportunity, and you have the typo bonus opportunity. But then on top of that, you're going to have an opportunity to earn bonus for what I call the word of the day. And so I'll explain this again next class, but what I'll be doing is just saying a word during class. I'll bring attention to it. In the middle of a lesson, I'll say, "Oh, and the word of the day is," and I'll have a little spreadsheet set up for you, or it'll be a spreadsheet for me, but you'll have a survey that you complete, and all you have to do is indicate the word. You just type in the word, and then use that word in a sentence, and I give you bonus credit for that too. And that one, it might not be obvious what the purpose is until I tell you that the offer for the bonus on that expires at the end of every class. So if I say the word of the day during the lecture, I'll only be accepting it right up until the end of class, and that'll be it. I usually give a few minutes after class is over, just because sometimes people are like, I can't stop listening just to do this word of the day thing. I'll try to do it later, and then they're worried that they're going to forget. But so I'll say, like in the middle of the lesson, I'll say, "Oh, by the way, the word of the day is jocular," and then you'll take that and put it into the survey that I'll have set up, and at the end of the semester, I give you bonus points for that. Right? So if you haven't figured out the point of that, I'll just flat out say it, just to see if people are paying attention. That's it. So I'll explain that one again, though, because we're not ready to do that tonight. But that's also a bonus opportunity. Oh, you got these like fun little bonus things for people to do. Yeah, I try to keep it simple. I also try to keep it like not math related, not too math related anyway, just because I figure, like it should be a reward for going above and beyond what's in the course, not necessarily just doing more course. So anyway, that's enough about that for now. Anyway, if you have questions on that, I can talk to you about it later. So in number 7, it says TI is congruent to ME, and we know that the measure of side ME or segment ME is 1 5/8. So the measure of TI is going to be 1 5/8. 1 5/8 inches. All right. This next little section is getting, I mean, this goes into the category of like, all right, this is borderline a little too obvious, hopefully. I mean, honestly, if I'm boring you to death, that's a little extreme. Boring you to tears with some of the stuff that we're talking about tonight, because you're like, oh man, I already know this stuff. Jeez, we're gonna spend the whole class on this. Honestly, that's probably a good thing, because we want to make sure that we're all on equal footing going into the course. But these are some things that they're foundational concepts that not everybody knows, and it's worth taking the time. But also, we're going to be using a lot of this stuff. It's going to be stuff that we have to take for granted going forward. Right? So, like something like, for example, the measure of the segment here, AC, is telling us to go from A to C all the way. Okay. So what does that mean? It's telling us if I want to go this entire distance, I'm going to have to take the 16.7 millimeters and add to it the 12.8 millimeters. All right. There's plenty of applications of stuff like this. If you need to measure something that's really lengthy, I mean, 16.7 millimeters is not really lengthy, but like if you have a measuring tape that's 12 feet long and you have to measure a room that you know is more than 12 feet long, then what do? Well, you go out a certain distance with your measuring tape, you mark a spot on the wall, on the floor, whatever, and then move your measuring tape to start at that mark and go the rest of the way, and then add those two values together. Okay, so that's a pretty straightforward application of this concept. All right, on Desmos, it's really just a matter, I mean, nothing fancy here. You're just taking the 16.7 and adding to it a 12.8. A nice feature of Desmos, so it's going to be 29.5 millimeters. A nice feature of Desmos, you see here on the left-hand side, a little fraction icon. And if you're one of those folks who likes the fraction form, when it's a 0.5, you can go either way. But if it's like a funky decimal and you see that little fraction icon, what that means is that if you tap on it, it'll convert your answer into fraction form. Right? Tap on it again, it goes back. Right? So if you have something like, 33 divided by 7, that's a pretty nasty decimal. So let's say you started a problem and you did all the work and you got that decimal form. If you see that fraction icon there on the side, you can tap on it and get something much more convenient to write. Because the thing is, we don't really, in geometry, we don't really want to get into rounding. So it's like, wait, we're not gonna round? Well, if we can avoid it, we're not gonna round. So if I have, this entire decimal here, let me just do it like this. Like I did some advanced computation and I came up with, of course it won't let me paste it now. All right, well, I'll just type something in. Let's say I came up with this decimal. That's a pretty lengthy decimal to write. Okay. And I don't want to round it, but the temptation is there. A number of times people just write 3.1 and I'll have to say, well, that's not right. It's not 3.1, it's something else. But if that fraction icon is right there, you just tap on it and you get, this is not a good example, obviously, but you get something more convenient to write down. well, something that you would not have to worry about rounding. I mean, it's true with this disgusting fraction, you wouldn't have to worry about rounding it, but that's not doing a good job of proving my point. Put it that way. But yeah, that's the idea. You just hit that little fraction. Let's see if I get a better one. 2 point. I'll just do 0.625. Keep it simple. All right. Then tap on that bad boy. 33 over 16. I'd rather write the 33 over 16 than 2.0625. Don't worry about rounding. Right, but to each their own. Now for number 9, I want S to T. So that's from here to here. So this distance. So that's like saying, all right, I know the room is 40 feet long. I'm just making up numbers now. I know the room is 40 feet long, and I only have a 12-foot ruler. So I go out 12 feet, whatever that remaining distance is, has to cover from the 12 feet to the 40 feet. So I would just subtract it. Say, okay, the rest of the distance is 28 feet, right? That's all that's happening here. Computationally, it's just 4.0 minus 1.2, or 4 minus 1.2, right? In which case you get 2.8 centimeters. All right, so a little addition, subtraction, stuff like that, but nothing too crazy. All right, so the remaining problems here involve actual measurement. So I have to, or at least the remaining problems and what we're going to do this evening, at least in part of the notes, they involve measurement in some capacity, like physical measurement. So it would be one of those cases where you either get a ruler out, hold it up to the screen and start measuring. That's assuming things are to scale. You can use a digital ruler. You could use other options also, which can be a little bit trickier, like Desmos and things like that. But I'm just going to show you using just an ordinary ruler, right? But before we do that, we'll do numbers 11 and 12. So I'll do 11, 12, and really 13, and then we'll take a little break, and then I'll get into the overview of the next assignment. Right. So it says point B for number 11. Point B is between A and C. Right. So start off. I personally would start off drawing a diagram. So we have point A going to point C. Very poor quality diagram. Let me just fix that. And point B is somewhere in between. I don't know where, so I can really just put it anywhere. But they do give me measurements. They tell me to measure from A to C is 32 millimeters. And A to B is 17. So I want to be kind of thinking about where, when I'm placing point B, I got to get 17 millimeters away from A, right? So half the distance here from A to C, that's going to be 16. Right? Now I'm just ballparking. I'll show you how to I'll show you ways to come up with the precise measurement down the line, but that's where 16 would be. So if I want to plot point B, I got to go somewhere to the right of that. So I'm looking at something in this neighborhood right here that I would call point B. Right, this distance here is going to be 17. And so what they're asking us for is the distance from B to C. So that's the remaining distance. Right, same idea. It's just subtraction. Right, except we had to come up with the diagram ourselves first. So 32 minus 17, 15 millimeters. That's going to be the measure of BC. All right. So you take the information you have. What do you know? What do you not know? And it's usually almost always either addition or subtraction. So point C is between A and B. Right? It's the same idea, except it's A and B that are the extremes. So start off with A here, bring it over to B. The benefit of geometry, Euclidean anyway, is that it doesn't really have to be a scale drawing as long as you have in just a spatial awareness. You know, it's just got to be kind of in the neighborhood, right? Because the labels kind of trump the actual distances, right? So they're saying from A to C is 3 1/8, and C to B is 2 1/16, right? And C is somewhere in this vicinity, right? So 3 1/8 is a little bit bigger than 2 1/16. So if I'm placing C, I would want to go a little bit more than halfway. So this one is the 3 1/8, and this is the 2 1/16. We just need to add those together, right? So we know that the 3 and the 2 added together is going to give us a 5, because ultimately we're looking. Oh, they said, oh, here's another typo.
I was just about to ask. Yeah, I was like, they already told us technically B.
Yeah, they gave us the answer. We're already done. And now it's supposed to be A to B. Yeah, so that should be A to B. All right. So we're going to take the sum of these two things. Now we know the 3 plus the 2 is going to give us a 5. So then I just have to add the 1/8 and the 1/16. You could use technology for that. You could also get a common denominator and put it all together there. But if I'm letting you use the technology, at least consider it, you know. So 1 divided by 8. You use division in Desmos to make fractions, right? I mean, you probably saw me doing it a couple times, but just to make sure I clearly state that, division, using that division key is what brings up a fraction pool, right? So then if I want to add two fractions, I would just say plus, and then I create another division with the 1/16. And then you get the 0.1875, right? And then convert it over into fraction form if you like, or leave it as a decimal. All right. The only issue would be is that the two fractions added to a value greater than 1, that might impact the overall total. But really, it's just a matter of saying, you know, I'm taking 5 and adding it to this measure. So 5 and 1.1875 added together. So 5.1875, or 5 and 3/16.
Did you just press enter?
Yeah, you just hit that little enter key, that little jammy here. The blue key. All right. We always want to have our units. And again, this is the measure of AB. All right. So then the remaining problems here, I mean, some folks are pencil paper kind of folks. That's okay. I mean, it would require you to print out some paperwork, but then you could slap a ruler on it and be fine. As far as a digital approach is concerned, really, as long as I know what instrument you used and what the precision was, then like answers can vary. You know, so you could have a bunch of different folks doing it a bunch of different ways, and then they'll all be right. So let me show you a digital approach, but it would require that you had an annotation app, right? But I'll also show you a way that you can do it on Desmos, right? But that's actually part of the explanation related to the assignment. So that's, you know, more on that in a little bit. All right. So for this, if you have an annotation app, this is the GoodNotes app. You could actually import the image of a ruler. Right. So this one says to do it in inches. So I have metric and I have standard units. So all I would do, and you see how you can resize it, which is the problem. So it's not going to be like accurate to whatever the actual units are. Now, like if somebody printed out this document and put an ordinary ruler on it, they're going to come up with a different value than what I would get if I enlarged this and measured it using these increments, right? But what I would do, because I don't want to have to print out stuff, and all I'm really asking you to do is demonstrate proficiency in using a measuring device. All I would do is I would import an image of a ruler, match it up to whatever it is I'm measuring, just like one of those problems that we worked on before. See? Take a look. It's almost there, kind of close. There we go. But then you'd actually leave the ruler. Leave the ruler. Oh, dang it. Get out of here. My orientation is a little off, so I'm just fixing it a little bit. There we go. So then I would say here, using this ruler, which has a precision. So we want to get into the precision of the ruler. All right. The ruler precision. So 1 unit, but then we have all these tick marks that make up that 1 unit. I want to know what 1 tick mark is worth. So I have 1, 2, 3, 4, 5, 6, 7, 8, 16 of those little tick marks. So each one of these tick marks is worth 1/16 of a unit. And the unit is inches, right? They told us to measure in inches, so there we go. So 1/16 of an inch. And so the distance here, well, I have 1, 2, 3, plus I'd have 1, 2, 3, 4, 5, 6, 7. It looks like 8. It looks like I'm right at 8. It's tough because it could be a smidge shorter, but it looks like I'm at 8 of those 1/16 of an inch. 8 times 1/16, sorry. 8 of means 8 times. All right, which amounts to 1/2. So 3 1/2 inches. All right, so that's the justification of the measurement. I mean, you also kind of look at it and say it's pretty clearly 3.5 inches, but this is the appropriate work, if you will. All right, so for a digital approach, you'd have to leave the ruler as part of the solution. Like, okay, so now I know that you use this ruler and this is what you got, so that when I measure it on paper and I get like 7 3/4 inches, and I'm like, well, that's way different from what you got. At least I know you did the measuring part of it correct. All right. So I know that's kind of weird. It's just sort of a concession for being in a digital environment. And if we were in person, I'd pass out rulers and be like, start measuring, folks, But I don't want to make people print out papers that they don't need to, So, and honestly, would you even? Some of you would, some of you wouldn't. Like, you got to print out all this stuff. It's like, yeah, I'll get right on that. Then I'm so anti-paper these days, and it's not even like an environmental concern, although that is part of it. Not for me anyway, but like it's a nice byproduct. It's just I don't want to carry papers around. I'm trying to lighten the load. My back is killing me. So, anytime you can digitize stuff, it's always preferred. Right. So, like I said, we'll take a little break, 5 minutes or so, So by this clock, as if we're in a classroom, around 7:45, we'll come back. I wanted to take you through the next assignment and then make sure that you have some time to work on some stuff at the end and ask questions. All right, so let me stop this recording.